All right. Hello, everybody. My name is Pamir. I'm a managing partner at Blackbird, and in this session, we have Jon Petersen of Archer, and Jon is the vice president of data science in the company. And what we'll be doing is we'll be talking about some data-driven decision-making when launching eVTOL networks over a given city. So welcome, Jon.
Thanks, Pamir. Delighted to be here.
Glad to have you here. Before we dive in, I just want to say I'm proud to share this stage with a fellow Yellow Jacket from Georgia Tech. And it seems like in the industry, there's some great engineers coming from our alma mater. So
couldn't have said it better myself. Go Jackets.
Go Jackets. That's right. Okay, so Jon, could you give us maybe a little bit about what you do for Archer and how you arrived professionally at optimizing for aerial mobility?
Yeah, happy to. So I have the great pleasure of leading an extraordinarily talented group of data scientists and engineers. It is our mandate to build technology that will help Archer arrive at really critical decisions well ahead of the first commercial flight. These decisions span the actual design of the aircraft, manufacturing, and then ultimately the operations. I suspect we can kind of go into depth a little later. But these existential questions are how we design a vehicle, how we bring it to market, what cities we select, what routes we select, et cetera. In terms of how I got here, I guess, long story short, I've been working in this industry since 2016. I was happily employed with Uber. I was working on the matching algorithm behind Uber Pool, if anyone's taken that. And then my love of technology and UAM came together in 2016, right before the Uber Elevate white paper was released. I was able to contribute a small part of that. Caught the UAM bug pretty early and have been pretty active in this space ever since.
Yeah, that's very cool. And as I understand, Archer is, you have this internal tool called the Prime Radiant. Maybe you can talk about this technology that you have and what kind of problem is this tool really solving?
Yeah, happy to. So let's see, I'll talk about what this tool is and then what the use cases are for applying this tool. In a nutshell, this tool is a system simulation engine that will essentially enable one to simulate an operational day of a UAM operation, flying our Midnight aircraft. And if you're not familiar, Midnight's the name of our one pilot plus 4 passenger seat aircraft that we intend to bring to market 2025. So let's see, what it is in a nutshell, we start, the atomic unit of all of the decision making really starts with how people are moving in cities today and how we anticipate them to move tomorrow. We care very deeply about really characterizing the spatio-temporal movement of trips in cities. Where are people traveling to, at what times of day, what is the purpose of trips, what mode of transport do they use, et cetera. And what we'll do is we'll build a lot of tools to try to identify that subset of trips that we think are addressable. And that involves trying to find trips that have, A, the potential for considerable time savings. That's, of course, part of our value prop. And then also trips that we believe are likely to have a willingness to pay, given a host of different attributes, for a service. There's also other things like experience, which we're really big on. Those are a little bit more qualitative than quantitative. But when we have that kind of set of addressable trips, those are the trips that we're trying to serve. We have the ability to build networks, describe networks, maybe a user inputs, here's a hypothetical network, how does this perform? Algorithmically, we can kind of identify zones in cities that we think are optimal for an urban air mobility operator. So that's, and then once the network is established, then we can kind of characterize the joint movement of aircraft, passengers, charging events, et cetera. So that's what the technology is. And how we use it is we like to ask, what if? What if we have 3 different vehicle specifications with different speed range and payload combinations? How do these perform on the network? How do the networks differ? We can use it to, I guess, describe things. Like we can try to predict the amount of power that we need at our vertiports. We use this sometimes to work with cities themselves. Seeing is believing, and while there's no substitute for seeing the aircraft and hearing it up close, we use our tool to inform policymakers in cities. They ask questions about, what is this going to do to my existing traffic in our cities? Are people going to be accessing your vertiports by car, by public transit? Are they going to be walking? And we also do some descriptive analytics around noise. And so this is pretty interesting as well, where we will oftentimes show policymakers what the impact is on the ambient noise level in cities when we layer our intended operations on top of that. So that helps kind of inform in both a kind of a descriptive and prescriptive manner. So we use this to size our aircraft, to formulate the basis of our go-to-market effort, our launch strategy, and then to address all sorts of questions. And this tool is really used, I think, in some capacity from virtually every team, from our vehicle engineering team, working very closely with our chief engineer, to our go-to-market team, our operations team, executives, and supply chain manufacturing, and so on.
So, thank you for the detail. I remember back in the Uber Elevate days, you guys had this, really cool visuals of the networks over LA and all kinds of demographic analysis. Is this a similar tool to that, or is it something a bit more sophisticated and advanced than that?
Yeah, I would say the inputs and outputs are not too dissimilar. I cannot speak to the state of that tool today, but yeah, it's not too dissimilar. I think under the hood, I think there's a lot of profound differences and use cases, but it's fairly similar at the 30,000-foot level.
Got it. And I imagine that other eVTOL players, especially let's say the leading ones, probably also have this kind of database analysis when they're planning to launch in a given region, right? But I just want to understand, with the capability that you have in-house, what unique advantage do you have against other eVTOL players who may or may not have this technology?
It's a good question. It's like we're Frosted Nixon up here. All right, so let's see. How would I answer that? All right, well, if you take the lens of a UAM operator, I think the two most important attributes that one has are the vehicle and the network. I think when you look back at traditional aviation, networks and vehicles are sized somewhat decoupled from one another, right? An aircraft OEM does not necessarily have perfect insight or even a say in where precisely that aircraft will be operating, with what frequency, et cetera. Conversely, aircraft operators cannot spec out every single attribute of the vehicle itself. So I think trying to size your aircraft and determining your networks in a kind of concurrent manner bring a substantial advantage. And I don't think we're the only player certainly doing that. I know other friends of ours in the industry are kind of approaching that in the same manner. But there are a lot of advantages from kind of starting from a clean sheet. I can kind of give you one quick example. So I'm not a vehicle design engineer, so I need to tread very carefully, especially with this crowd. But the vehicle design space is rife with all sorts of interesting trades. Chief among them is the speed, range, and payload of an aircraft. These are existential questions, and they're not trivial. I mean, there's a very broad spectrum of how different OEMs are designing their aircraft. When we started, the first thing we looked at was, okay, what is the anticipated payload? We started looking at a 1+1 all the way through up a 1+4 aircraft. And if we want to try to assert with some degree of confidence that that fourth passenger seat is indeed desired, we have to have a pretty good idea of the networks for which we'll operate, both in near term and at scale. And that's just kind of one example. And that's going to depend upon where you wish to operate, in which cities, which routes, et cetera. Now, of course, we call this a trade space, right? So that additional seat in the vehicle needs to be paid in somehow. And usually this can be done by sacrificing range or speed, right? And so that's why it's such an interesting problem, is it's just rife with all sorts of different trade-offs here. So what we will do is we will work very closely with our chief engineer. We spec'd out hundreds of different viable designs of our aircraft. We would simulate them through the network. And if you think of the trade space as a triangle, where you have vertices from the speed, range, and payload, our question was, where in the triangle do we want to be? I'm not saying that this is the only way for which we arrived at our design decision, but it was certainly a strong influential manner from which culminated in our Midnight aircraft design.
Yeah, so I guess the analogy in startups or software is basically you have this tool to ensure product market fit without ever going to market, because the constraint here is that you can't really take the vehicle out there and actually test with users and passengers and in the market and iterate, which is what really happens in software, right? So seems incredibly important to get this product market fit correctly down the line. So
Agreed.
cool. Okay. So I want to understand some of the criteria that you guys use to understand what is a good city to launch at and what is a bad city to launch at. Like, what are some variables and parameters that are really important to this model, essentially making, enabling you to do a big business decision years down the line?
Yeah, that's a great question. Okay, so city selection. So we kind of start again from kind of a clean sheet. There's kind of this bottoms-up approach that I mentioned earlier, using our technology to assess a market. But there's also kind of a top-down element as well. And so what we will do is we'll characterize, a large number of cities, and there's all sorts of different dimensions to what, how we think about launching a UAM operation in the city. So what do we care about? Well, naturally, we care about things like how many people live in or around that region, what the growth trajectories were the past 10 years and what they are expected to be the next 10 years. We naturally look a lot at traffic patterns, how congested are cities, how, other modes of transport that may or may not be available. So yeah, that's kind of on the trip side. We look a lot at existing aviation infrastructure. We are of the mind that a lot of our early launch networks in our crawl phase will rely on existing aviation infrastructure. And so we'll try to characterize the set of GA airports, commercial airports, any heliports that might exist currently, et cetera. There's a host of weather and operational criteria. Naturally, we want to estimate the VFR uptime. We want to look at the probability that you have a flight into known icing, for which we will not operate on day one, certainly. Weather wind impact is important as well. So knowing what routes are likely to fly, what we will need to do is to assess the sensitivity to a headwind for our longer range missions, for instance, to estimate how frequently those will be available. Naturally, there's questions about power availability at sites, et cetera. So these are all, fairly quantitative measures. There's a lot of qualitative measures as well. Political willingness. There are, experiences in cities. So one of the challenges here is we have to kind of blend an art and a science to this. And so you can almost think about it, as a scorecard. And every dimension of this gets you can think about it as getting a weight. And then what we'll do is we'll kind of look at the cities for which we desire to operate, top down. We will look at our bottoms-up modeling. If we did launch in a city, what is the expected fleet size? How do the networks look? How many vertiports are needed to sustain an early operation on day one? And we'll kind of marry the two and try to construct a vehicle deployment plan that adheres to both, if that makes sense.
I understand. Yeah, and when you look at, let's say, 10, 15, 20 cities, 30 cities, what typically pops up as the biggest blocker for you when you're trying to optimize the network? What is usually the big constraint or constraints that you face?
Yeah, are you referring to particularly in terms of serving meaningful throughputs or high demand, things like that?
Yeah, essentially the go, no-go decision for a specific city. It could be the infrastructure, the airspace, right?
Yeah, a lot of this is infrastructure, right, related. I think one of the, there are a number of barriers, but one of the major barriers to really making a city exciting and having a thriving UAM ecosystem, I believe involves infrastructure, right? And it's no surprise that, there's this really interesting challenge where oftentimes, in many cities where you desire high throughput, are kind of correspond to the areas that are most difficult to launch a vertiport, right? In city centers or large, dense commercial airports with a complicated NAS, et cetera. So a lot of this revolves around our ability to kind of scale in some sense. And so a lot of this comes down to vertiports. I get more excited with, what we oftentimes find is that networks with fewer vertiports but higher throughput capacity are healthier than a city with just has a saturation of vertiports everywhere.
Oh, wow. Interesting. Okay. So yes, I think we dived into the quantitative details really well, so thank you so much for that. Maybe we can paint a picture for our audience here. Maybe, when you guys launch, how the initial route structures will look, the network structure, operations. Like, can you give us a feel of maybe like a day in the life of a Archer network in one of your launch cities?
Sure. Okay, good question. So one of the attributes about Archer is we are just laser focused on bringing this to market. We're here for the end game. That's the scaled operation. That was, the basis of a lot of talks earlier today, which gets me excited. Me personally, it wasn't the existence of the technology that made me excited with UAM. It was that kind of that path to scalability that really inspired me. But there's a saying: if you can dodge a wrench, you can dodge a ball. So we're trying to form that primitive operation initially. So I think what you're going to see in early years is I think we have to be very realistic, right? I think it's going to be very modest in 2025, very modest. I think you're going to see most vertiports that are going to probably correspond to existing GA airports. I mean, there might be some commercial airports, certainly. We've made one announcement, a couple of announcements already. So I think you're going to see a lot of kind of what exists today, right? That's not necessarily the most exciting things when you see these really cool renderings of these future concepts of vertiports, but it's going to take a long time for those to mature, relatively long time. I think you're going to see relatively modest operations, modest flights. I think you're going to see very conservative operations when a flight is dispatched. I think you're going to see conservative policies around not dispatching until you're absolutely certain that there exists a capacity at your arrival vertiport. Naturally, as was stated earlier today, the plans in the FAA ConOps 2.0 are going to be using existing ATC today, which makes sense. And I think also on the experience side, kind of going back to that again, I think what you're going to see is, maybe load factors, maybe vehicle utilization not be quite as high as what makes our CFO happy, because we want to really nail the experience and we want to be very driven, especially with our early adapters. So I think that's kind of the crawl phase as we see it at a very high level.
Perfect. So I think we have some questions from the audience. Before we go to the Slido, anybody have in-person questions with a microphone they want to ask? All right, so let's go into Slido. I guess the first question is from Garrett Rhyme of Aviation Week. How many hours have you flight tested the Maker eVTOL, and how does that data from those flights inform your Prime Radiant tool?
It's a good question. It's one I am going to probably have to defer to just because I'm not intricately involved with the Maker program. I cannot give an exact estimate. You're certainly welcome to reach out to our comms department for that. In terms of learnings, honestly, the tool that I've discussed is really around our midnight aircraft. There are some learnings that we've been getting from our aero models that kind of influence the Prime Radiant in terms of how much discharge we estimate for every mission we fly. So there was some feedback there, but it's largely decoupled from Maker.
All right. How big compute engine you need to run this simulator? I guess this is a GPU question.
Yeah, that's a good question. So just to kind of give an example, I mean, in the greater New York City region, there are somewhere on the order of maybe 40 million trips that happen every day. It's even higher than that in the greater Los Angeles region. And we actually look at each individual trip. We fuse about 20-ish data sources together from ops and from the FAA, et cetera. And so when you just think of this kind of the combinatorics of the problem, there's about roughly 30 GA airports, commercial airports, and existing heliports in the greater New York City area. There's far more than that, but the ones that we think might be amenable to an early UAM operation are approximately 30. So if we want roughly 8 of these sites to be stood up, I don't know the number off the top of my head right now, but it's something like 6 million. So there's a lot of different combinations. So yeah, I mean, we work closely with our cloud partners to really try to scale this up. It's a pretty compute heavy, but it's offline. We're also getting into the kind of the online world of flight operations, which has to be far more, computationally tractable. But yeah, we work with our cloud partners pretty carefully to make this somewhat tractable.
And we're not really talking about like, it's not like training a foundational model or a large language model, right? This is, I guess you do have some machine learning integrated, but it's nothing on the scale of let's say ChatGPT or something like that?
Yeah, that's correct. It's large, it's not trivial, but it's nothing of the orders of what you see from LLMs today.
Got it. Okay, so we have 1 more minute. Maybe to conclude this phase of this session, I just want to ask you if you have, let's say, one main critical message for the industry, like something that maybe how can others in this audience support you in your goals and make Archer, achieve their goals?
Yeah, a good question. There's a lot of uncertainty in this space. No one knows exactly how the flying public will respond to this technology. No one can predict with precision what policies, what regs exist in the future. And I think it's tempting to not make data-driven decisions because it's very difficult to assess data when you don't have a service. But we actually take kind of the opposite view, and we think that precisely because there's so much uncertainty, that we need data-driven technologies to build what we call robust decisions. These are decisions that have to be robust to so much uncertainty in this process. And that way, we think that the solutions that we're achieving, our go-to-market strategy, our aircraft is designed with uncertainty in mind. And so I would certainly encourage everyone to hire a data science team, embrace the complexity associated with having so much uncertainty in this space.